I'm Yannick Arnoux, and I'm working as a physicist in a laboratoire de physique subatomique et de cosmologie. And I'm also teaching medical physics in Université Grenoble-Alpes. Today I will be talking to you about radiotherapy, a tiny portion of radiotherapy, and it will be about the monitoring of the dose in high dose rate treatments. We are going to talk about cancer, and cancer, what does it look like? There you see some cells that are turning crazy. Normal cells are dividing from time to time. They got, let's say, food brought by blood vessels. And those bad guys here, they are, let's say, clever enough or crazy enough to divide crazily. So in a short time range, there will be a huge amount of numerous cells. And in addition, they are able to send signals such that blood vessels will grow to feed them and to bring them more energy. There you see the chest of a guy. Have a look at his lungs and what's going on inside. There are cells, normal cells, light color, everything is fine. And there we are entering the nucleus of a cell, and we see a DNA strand which is opening for replication or whatever. And if many things happen wrong in the DNA, there can be some craziness going into the cell replication which is no more controlled. There you see one of those crazy cells who has entered the bloodstream and who is now running to the body, and it can sometimes escape elsewhere. And this will lead to metastasis, cancer going in another place, here in the brain. What can we do to cure this cancer? Let's say that here we have a patient and there is a tumor in the lung. Maybe not so visible from what you can see. If we got a clearer picture, lighter picture, yes, maybe you can see here some suspicious stuff just in the dotted area, inside the dotted area. So we will have that. There is a tumor in the lung and we want to destroy it. How can we destroy it? Well, we can use some radiotherapy. So radiotherapy is about delivering dose. So dose is basically the amount of energy that will be deposited into the tumor. This dose, the unit is gray, and let's say that here for this particular tumor, something like 30 to 40 grays will be big enough to kill the tumor. And you've got this sigmoid curve going from 0 to 1, and on the vertical axis you've got the tumor control probability, which is basically the probability that the tumor will be killed, that the tumor will not survive to the treatment. So it's good. Let's burn the tumor. Let's put a maximum of dose in the tumor. Well, you have to slow down a little bit and to look at the way normal tissue will be affected by the treatments you want to deliver. And there on the other side, you see the normal tissue complication probability, which is the probability that the treatment will damage the good cell. And you see, it's also a sigmoid function going from 0, everything is 5, to 1, everything goes wrong. And both curves, both sigmoids look alike, and they are very close. They are parallel, let's say. So there is a small window in between, and you have to go through compromises. Compromises like the tumor control. You want to have it as high as possible, but the normal tissue complication, you want to have it as low as possible. So you have to be in the middle, let's say using the blue curve, where you take into account how good you can treat the tumor and how good you will spare the normal tissue. And the window is rather small. Overdosage by, let's say, more than 5%, it will affect too much the normal tissue, and it might trigger some future cancer being brought to the normal tissue due to irradiation, so it's not good. If you go too low, then the tumor will keep on growing, so it's not good either. And so this window is rather small, so you have to be lying where you should be. And you have to be very accurate, and you know that within one treatment, you will not be able to kill the tumor because you are not in the 100% probability area. What can you do? There is indeed a nice feature when you compare normal tissue and tumor. Normal tissue is pretty good at self-repairing if its DNA is affected. On the other side, tumor is very good at multiplying itself, but not at all at self-repairing. And this is good because we can trigger something like a differential response to the radiation. Let's add more material to this picture. Oh my god, so many curves. What do we have? We have at the beginning versus time. Time is the x-axis and the number of cell, the y-axis. Okay, we've got a stable, steady population of normal tissue. Then on, let's say, on the first day of the treatment, those cells will receive some X-ray due to radiotherapy. So the population will be affected. On the other side, we've got tumor cells, and they are getting crazy. They are increasing their number, and on the same day, they receive their X-ray, and the population will fall down. But during the next 2 days, normal tissue will recover pretty well, and tumor tissue will not recover so well. And if you repeat these treatments day after day, you see that normal tissue population will indeed drop down, but at the end, it will be able to recover as it was at the very beginning, and on the tumor side, it will keep on falling down until you are pretty sure that there is nobody left. So you've got a differential response to the radiation, but you need to perform several sessions of beam delivery of irradiations. How do you perform those irradiation? You need a compact linear accelerator, which is called LINAC. It can deliver electron beams from, let's say, 4 to 20 MeV, or it can also deliver photon beams from, let's say, 4 to 20 megavolts, not MeV, megavolts. Okay. Let's see at what it looks. There is a person here, and a beam will be sent into its body. So you see, well, X-ray are not yellow, but you see a beam coming out of the LINAC head, and you need every 2 days to deliver the prescribed dose into the tumor exactly at the same location to be sure to target properly the tumor. First, you don't blindly irradiate a patient. You need first to localize the tumor and the other organs in an anatomic model you will build from a CT scan. So you've got a CT scan from your patient, and you are able to localize the tumor from and other organs surrounding the tumor, the targeted tumor. And then you will run a computer simulation to see how you can adjust the different beams such that with different entry points, you will be able to accumulate, to concentrate energy in the target, and to spare as much as you can the surrounding tissue. Such that you will match the dose prescription from the radiotherapist. To deliver the beam, we need a LINAC. So let's have a look at what's inside a LINAC. Let's zoom in and see the main component of a LINAC that will provide beam exiting from the head. So you see that we have different parts in the LINAC. We will shortly review them. And starting from the right, we have an electron gun, so it just provides electron. Then there is a radio frequency accelerating cavity that will, let's say, accelerate electrons to 6 MeV. At the end of this RF accelerating cavity, the electrons will exit with a huge, large energy and they will be bent by magnets, 1, 2, 3 magnets, such that the beam now is pointing downwards where there is the patient. And usually we don't treat patient with electron beams but with X-rays, and for that we need a kind of device to transform the beam, and this is just a target. Due to Bremsstrahlung, electron beam will give birth to X-rays, and those X-rays will be sent to the patient, and there is an important device we will comment on later, which is the monitoring ion chamber. Okay, so we've got the beam from the LINAC. It's good. The LINAC head will be able to rotate around the patients to have those multiple entry points to deliver the correct dose in the tumor while sparing the surrounding tissues. Good. And we know that, as said by the radiotherapist, each session should target at 2 grays being delivered into the tumor. 2 grays. By the way, can we spend some time on what is a gray? If we look at the definition, a gray is the absorption of 1 joule of radiation energy per kilogram of matter. Okay, if we take a kilogram of matter, that would be water. This radiation will produce in the target ionization mostly, but also excitations of the molecules, of the electronics layers of the molecules, and there will be also small energy transfers. But those 3 components will contribute to the absorbed energy. Okay, so we say the dose is the energy being absorbed by the target divided by the mass of the target, D equal E divided by M. Okay. We said, yes, we have to burn the tumor easily, don't go too fast. And we know for sure that also dose will increase its temperature, because if we turn to thermodynamics, we know also that if you add to a mass, a target mass, some energy, then you will have an increase of its temperature, and there is a coefficient which relates both quantities. This coefficient, Cp, is a specific heat at constant pressure, and we've seen before that the dose is the energy divided by the mass, and the same energy will also have an effect on the temperature in the target. And if you combine both equations, you see that the rise of temperature can be the energy, but the energy is the dose times the mass divided by Cp times m. Okay. In a nutshell, the rise in temperature, it's just the dose divided by the specific heat of the target. Okay, so we say that delivering dose will rise the temperature of the target, of the tissue. If we take water as an example, Cp is something like 4,000 joules per kilogram per degree. And if you assume that you are treating a water target, to have an increase of 1 degree, which is not a lot, you need to deliver a dose of 4,000 grays. And you remember when we were talking about irradiation, we said 2 grays per delivery session. So this is a huge, huge amount. You may know that if the whole body of a human being is being irradiated, the median lethal dose is 5 grays, just 5 grays. So with this small amount of dose, you've got a 50% probability of dying. When you are treating a tumor, you will concentrate this dose in a very tiny portion of the body where is localized the tumor. And as a matter of fact, it will be very concentrated, but not enough to burn the target tumor. But you will have a very strong biological response. So even with tiny amounts of energy, tiny in the sense that it will not affect the temperature, the overall temperature of the target, but still you will have a strong biological response. And you have to be very careful because you are playing with very tiny amounts of energy and you will trigger very strong response on the biological side. So the beam properties, they have to be under very close control. And dosimetry is the art, let's say the art, of the measurement of the amount of radiation which is absorbed by a target. Let's have a look at a typical device for measuring the dose. There you see we have a chamber, so it's a gaseous chamber, it's a gaseous detector, which is used for absolute dosimetry in so-called high energy photon, electrons and proton beams. Okay. So you need to make it work, you need to apply an external voltage, okay, a few hundred volts. It can be used, this detector can be used to detect photons, electrons or protons from up to some MeV or hundreds of MeV kinetic energy, okay. It has a small sensitive volume, a portion of a cubic centimeter, and it's vented to air, meaning that air is running through the detector. Normal air, it's not a sealed detector, it's just connected to the external atmosphere. And ions will be created in the sensitive volume of the chamber, and it has this collection time. And the reference radiation, you need a reference because this detector is used for absolute dosimetry, so it will give you a number you can rely on. And this reference radiation is cobalt-60, a very known radioactive element. You will also need to perform dosimetry a water phantom. And so why do we need that? Because human body is often considered as water. Human body equal water. And this device will be very handy for studying the dose being deposited by a beam into what will be a human body, but there's just water, much easy. How do you use it? Well, you take your water tank and you align it. You have to be very accurate. You align it, you center it under the linac head, okay? And there you see a guy which is doing this very accurate measurement, but at the beginning this guy needs to put in place an ionization chamber. So it can be ionization chamber can be looking like this one, or a pinpoint, a very small tiny one, that one. And you see that this chamber is connected to let's say a tray. And this tray here, this guy here, it can allow displacement into X, also Y, and it can also dive, and Z, X, Y, Z, such by using a radiation beam and moving the chamber from places to places, it will take time, you will be able to record the dose being delivered into each and every point in the water tank. So what do we have? You see there some results of the dosimetry. So this is the z-axis, the depth axis, and the field that has been used here might be something like, let's say, a 5 by 5, a 5 centimeter wide beam. Okay, you see that if you look at the dose with respect to the depth here, it will rise up, then fall down due to the beam absorption by the water. And if you look at the lateral profile, you will see that you have almost no dose on the side, and it starts to rise up, gets its maximum, then falls down on the other side. Okay, and when you increase the side of the beam, let's say from 5 to 10 centimeter, you keep on having the same shape in the central line, and you have different shape as you expect in the lateral profile. Usually people are using a solid state phantom because it's much easier, much quicker than to fill the water tank, to align it. There you have almost to the same accuracy, you have almost the same result using plates of PMMA or RW3, which is known as a solid water phantom, and you have the same results. Ionization chamber, the guy that is inserted here, how do they work? You've seen that normally some weeks ago. It's gaseous detector, the different way you can use them depending on the difference of potential you will apply on the electrodes. And usually people in particle physics, they are using gaseous detector into proportional counter mode or maybe Geiger-Müller counter mode. But ionization chamber, you will not multiply the particle, you will just collect them. Basically an ionization chamber is just two polarized electrodes, and in between you have some gas between the electrodes, that's it. And you've got some polarization and you've got something to collect the charges. What's going on? Between those electrons you've got gas, and let's consider a photon beam that crosses this detector. You will get electrons due to photoelectric effect, Compton scattering, pair creation along the track of the photons, along the photons. And you will produce electrons, primary electrons that are fast particles. And along those particles, those fast electrons, you will have ionization, and you will produce positive ions mostly and slow electrons. So you've got positive ions and slow electrons. Good. And you expect the ionization to be proportional to the energy deposited by the beam in the enclosure here. Usually, electrons are quickly attached because you have using air as a gas. So electrons will be attached by molecules which likes electrons, like oxygen, nitrogen, all those guys. And quickly, very quickly, just much faster than it takes for the time it takes for an electron to drift towards the proper electrode, the electron will be attached. And sometimes it can also happen that an electron will pass by a positive ion and both guys can recombine. Okay. But what you have to know is basically in this ionization chamber, which uses air as a medium, you have mostly positive and negative ions drifting. And this signal, those particles drifting will induce current into the external circuits, and those charges will be collected by an electrometer. And so there you see we've got ionization chamber, cable, and electrometer on the other side. When we irradiate, it will take time, but we will collect some charges. Let's say here 300 picocoulombs. And we can be wondering how can we have the correspondence between those picocoulombs and how many grays did the chamber receive? And this is calibration, dosimetry calibration. How do we calibrate those chambers? To calibrate those chambers, we need proper element, and this proper element, reference element, is graphite. Calorimeters are made out of graphite because it's very nice. All the energy from the beam will be converted just and only into heat. You know that when irradiating some piece of equipment, it will rise its temperature even by a very tiny amount. But if you are accurate enough, you will take this rise in temperature as a measurement, a very precise measurement of the energy being injected into the elements. And you've got the same constant as before here, so you have to take into account the graphite constant. You know that the energy, if you are using, it can be a beam, or if you have a reference element such that the cobalt-60 radioactive elements, you will start irradiating, then you will stop irradiating. You've got the activity of the guy, and you've got a portion of the particles emitted, the photons emitted by the cobalt-60 that will reach your detector. So you have to be very accurate on what you are doing. But at the end, you know precisely by measuring the rise in temperature in your target, the amount of energy that was delivered to your target. And if you remember the previous equation we've seen, you also know that the dose is proportional to the rise in temperature. So now we've got everything. We measure how long it takes to get a given number of grays into the calorimeter, and you know it because it's proportional to the rise of temperature. And once you get the proper dose into your calorimeter, you stop the irradiation. And let's say that it took 15 seconds to get a given amount of grays into this calorimeter. Now what you do, you replace this calorimeter with your water phantom, and in addition you put inside your reference probe, your reference ionization chamber. And you will irradiate this ionization chamber during the same amount of time. And you know that what you will get from this ionization chamber is a given amount of charges of, let's say, picocoulomb. You read the accumulated charge, and now you just have to match how many charges are connected to how many grays, and you've got your calibration coefficient. Now that your dosimetric chain is calibrated, well, you can use it for measurement, so you can place your ionization chamber under the LINAC head, switch on the beam, and then collect the charges, integrate the charges, and at the end you will apply the coefficient to get the grays from the charges you got from the electrometer. We did that kind of study some years ago. We were working late at night in the Grenoble Public Hospital radiotherapy room, one of the rooms, and we had kind of ionization chamber, segmented ionization chamber with many pixels on it, connected to an acquisition setup, recording device, and this device was able to acquire in real time the beam characteristics from the LINAC head, and this is what it looks like. So in the x-axis you've got the time in milliseconds, portion of milliseconds, and you've got amplitude in arbitrary units, amplitude which is coming from what pixel of our pixelated ionization chamber. And you see that we've got pulses. So the beam is not constant, it's a pulsed beam. The beam that comes out of a LINAC head is pulsed. And you can see that the height of each and every pulse is different. It's a kind of live device. There is a feedback in it. And the idea is to, when you accumulate, when you zoom out to the previous plot, when you accumulate all the pulses, you expect that the sum of all the intensity from the pulses will match the prescribed dose. And there you see one recording, many pulses, rather stable, and another recording taken later on, which doesn't look at all as the previous one. The beam started to deliver power, real power, then the power dropped down. Still you had some spikes, low power, and then it was increasing again, and maybe overpower pulses to compensate for the previous lack of power before here. So you see that LINAC is not something which is stable. And you need to monitor constantly and as accurately as possible the beam properties throughout the beam delivery. And you have to do that in real time. Okay, now we've talked about calibration and we want to irradiate a real, genuine patient. And when you do that, you cannot control using a water tank and a ionization chamber if the delivered dose is correct or not. You have to use another device such that the patient will receive the proper treatment that you cannot control with a water tank and an ionization chamber. So how do you do that? Well, if you remember, at the end of the LINAC head, the beam is passing through ionization, as a matter of fact, a pair of ionization chambers. There are two of them for redundancy purposes. And this guy, this double guy here, is also known as a monitor chamber. And it's a gaseous detector that will provide charges when crossed by ionizing radiation. And what you do during the LINAC commissioning is you perform a calibration of this ion chamber. So you are using a calibrated ion chamber at the end of the beam, and you switch on the beam and you are collecting charges there until you reach a given amount of charges, which is equivalent to 1 hundredth of gray, 1 centigrade. And at the same time, you will collect the charges from the ion chamber, from the monitor chamber here. And by integrating those charges, you will establish a match between those charges and 1 centigrade in the dosimeter. And this amount of charges is called 1 monitor unit. So it's an arbitrary unit, and it's called 1 monitor unit. And after that, you can remove this device here. You know that once the needed amount of charges have been collected, you would have had 1 centigrade there. So your detector, your LINAC head now is calibrated, and you are able to talk in 2 monitor units, which are equivalent to 1 centigrade. Let's say that you want to deliver 200 monitor units because you want to have a dose of 200 centigrades, which are 2 grays, delivered in the target. So what do? You switch on the beam, and in the beam path you've got those two guys, those two ionization chamber, and they are collecting charges. So this is what you want to reach, and you have double readings such that even if one is failing, sooner or later you will reach the dose. You have to be careful when you're irradiating a patient, and then the beam is stopped. This is the way people are doing to irradiate and to deliver exactly 2 grays to the patient. You can see here such a double ionization chamber. There you've got, let's say, the upper electrode, the lower electrodes. I said electrodes because there are 2 of them here, 2 of them here, and you've got a mid plane because you have to apply voltage between the reference plane and electrodes. And you expect the beam, if it's properly steered, you expect the beam to be in the middle here, so there will be as many charges collected on the top electrode as on the bottom electrode, and expect the same. If the beam is well centered, it will create as many charges on the left part and on the right part of the lower electrodes. And as a matter of fact, the double chamber is created when you assemble all those 3 parts. You leave this one on the lower part, you put this one on the top of it, you reverse this one and you cover it, and then you've got your chamber. And there you've got some device to connect to air, because it's an air vented chamber, and you have electrodes, so you've got also some electrical wires, which we don't see here. Maybe you remember this, yes, for sure, you remember this slide where we had the pulses delivered by the LINAC versus time. And, well, basically the height of the pulse is something which is related to the dose rate. The higher the altitude of the pulse, the more the dose rate is. And, of course, the sum of the pulses has to match the prescribed dose. So let's say, just for the sake of it, that the two gray we want to deliver, they are into the shape of 2000 pulses, and each pulse is more or less 0.1 centigrade each. Okay. What if we were to change that to just 3 pulses of 0.67 gray each? What would happen? In order to answer this question, well, first we need to close the first part of this presentation, and we have almost reached the end, such that we will stop now talking about beam monitoring in conventional radiotherapy, conventional meaning low dose rate. In this first part, many things were oversimplified. I'm really sorry to have to go through so many approximations, and some of my explanations were really borderline. But the aim was that you got a feeling of the overall picture. Now we'll be shortly talking about beam monitoring in high dose rate radiotherapy. And if I want to make it short, it's not ready yet. There are many people working on it, and it's not ready, but it's almost done, and it's very promising. Not almost done, it's on its way. We'll be talking about flash therapy. You remember changing 2000 pulses of low dose rate to just a few of them at high dose rate. Typically, people say that flash effect, we will see what it is, occurs when the dose rate of a pulse is greater than 0.6 gray per pulse. So when the dose per beam pulse goes over this dashed line, we enter the flash effect. And you see that with conventional radiotherapy, we are far below, orders of magnitude below the flash effect. The other red dotted line here stands for the limit for conventional ionization chambers. They can be working up to there, but after that they are no more reliable. And this is indeed a problem for dosimetry. So what is this ultra high pulse dose rate stuff? What is flash therapy? On this slide I took from Anna Sebil, we've got all interesting information. We've got the fibrosis, we've got the pig, we've got human, and we've got some curves, TCP and NTCP curves. Let's go through each of them. The mouse. In 2014, Vincent Favaudon and his team used a specific LINAC, high dose rate LINAC, to irradiate mice. And it appeared that a side effect of irradiation in the lung is the creation of fibrosis. And fibrosis is scar tissue which is created after in response to an inflammatory process. So if you are to irradiate mice with a low dose rate, you will have a lot of fibrosis. If you are to irradiate the same mice with a very high dose rate beam, you can compare the difference. It's a factor of 200. It's 200 more powerful. If you are to irradiate to deliver the same dose to those mice with a high dose rate beam, the fibrosis is much reduced. So it can mean that the inflammatory process that affects normal cell is reduced if you are using high dose rate. This was the first hint. Then people went through that, and in 2019, well, it was in 2019, yes, they irradiated the skin of a pig using conventional beam, so low dose rate, average dose rate was 5 gray per minute. And you see there 3 points that were treated using electron beam, so overall dose delivered 34 grays, 31, 28. And this is what the skin looks like 36 weeks after the radiotherapy delivery session. So the skin is basically dead, it's dead tissue. Elsewhere, the same dose was delivered, but so the same total dose was delivered on the skin, but using flash with very high dose rate per pulse. And you can see that the skin has completely recovered. So what happened in the mouse? No more fibrosis, or much reduced, can also be seen on the skin of the pig. Then there was this paper, this first ever human patient being treated with high dose rate beams, electron beams. You can see here lymphoma on the skin, so cancer on the skin. And the patient has been treated with some pulses delivered by high dose rate LINAC, electron beam, and you see that after 3 weeks everything is almost now normal, and after 5 months it looks really pretty good. So it seems to be promising because there are no side effects on the skin so far. And you can see that on the tumor control probability, which doesn't change, but the normal tissue complication probability is shifted far on the right. So it looks good because the window for curing the cancer is much broader, much wider. It's really cool. But for sure, there might be something not so easy to go with it. Let's say you remember, the community agrees on the fact that flash effect occurs somehow above 0.6 gray per pulse. And it takes a small portion of a second at this dose rate, at this very high dose rate, to deliver the 2 grays. And let's see what you would expect from an ionization chamber or monitor chamber that is embedded into the head of the LINAC. Let's say that you plan to have 3 equal first intense pulses, followed by what is needed to reach the 2 grays. So 0.6, 1.2, 1.8, and then the remaining 0.2 grays to reach the 2 grays. So this is what is planned, and the machine is alive, it's breathing. Sometimes it does too much, sometimes it does too few, and it has to be in a feedback loop such that at the end you will reach 2 grays. Let's say that the first pulse is a bit too high. Then one has to compensate in the second pulse, so there has to be some real-time computation to adjust the second pulse, but it's a bit too low. No, still we are a bit too much compared to what we should have. And then we give a little less to reach 1.77, and in real time you have to compute for the remaining pulse to reach the 2 grays. So you have to be very accurate from the beginning and to do all that in real time. The problem is that when you are entering the high pulse, high dose rate pulse beam dosimetry, the common ionization chamber which are the reference instruments, they can no more be used because of saturation occurring. And this is indeed a big problem. And you know that along the track, the electrons, the fast electrons tracks, there are charges being generated, plus ions and electrons that will combine to molecules, such that you will have positive ions and negative ions. And if you look at the huge amount of particles, charged particles, who are generated in between the electrodes, it's so big that they will have sizable probability to recombine before reaching the electrodes. And the consequence of that is that we are losing charges. And losing charges means that the charges being collected by the electrometer connected to the ionization chamber, those charges, they are no more proportional to the intensity of the beam. So we are losing information, and we are no more in a linear process. The charges are no more linearly proportional to the dose being delivered. And it's really tricky to compensate for the loss of linearity. And the effect is rather big. If you see that when conventional ionization chambers are working, which is up to a dose per pulse, which is on the order of 10 to the minus 2, it's working fine. The ionization chamber are collecting 100% of the generated charges. But when you are increasing the dose rate per pulse, it can drop down so sharply that maybe at the end, people have performed some measurements. You are able to collect something like only 10% of the expected charges. So you are really losing a lot. And there you see a nice fit on the data points. So it's good. You can say maybe you can compensate, but no, it's really not easy to be accurate enough. You know that you have to be very precise when you are doing dosimetry. And you cannot play by compensating something which is too tricky it's not accurate enough. So things have to be done. People are working on that, so you can do not real-time measurement for sure. There are some radiochromic films. When being not exposed, they have this yellowish color, and this yellowish color can be splitted into red component, green component, and blue component. And you see that if you take similar strips and you irradiate them, increasing the dose, you can see that it turns to something more and more in the blue side. And you can draw from that calibration curves depending on the monitor units or the dose you've been irradiating those strips. The density, the optical density will change. It will turn to dark strips. And this can be used for measuring the dose that has been delivered even by very high dose rates beams. The problem with such films is that it takes several hours to stabilize after irradiation, and you need to be, and it takes time to get the readings, so you cannot use them in real time. People are also using aligning system in which electrons' property in molecules are affected by the dose being delivered. So it's another way of measuring the dose, but once again, it doesn't happen in real time. So this is really a limitation for this new way of curing cancer, high dose rate flash effect. And at the present time, there are no active dosimeters, and it's really a pain because you have to rely 100% on the behavior of the machine. And we've seen before that LINAC can oscillate or can start normally, or sometimes it drops down, then it goes again into bringing power, so you don't know what to do. And it's so powerful, this flash effect, that you are really have to be careful. So people are working on that. To me, clearly, it will be the next evolution in radiotherapy, and because there is a clear reduction of the complication on the normal tissue side. Okay. Many people are working on it all over the planet. It looks very promising, and some people, an Italian team, if I'm not mistaken, have designed a small ionization chamber with a small gap between electrodes. And this prototype might be very promising because the correction factor is close to 1, which means the charge you are collecting are 1 over this number here. So you are almost collecting 100% of charges. It looks good. Maybe people are on the edge of designing detectors that could be used for monitoring beams and controlling beams in real time. Many things still have to be done. First, you need to define a reference procedure to have a gray, but in high dose rate conditions. What is a gray? How can you, from different laboratories in the world, define a common gray all over the world? You need also to develop those detectors for real-time measurement. For real-time measurement, and to control the LINAC, to have something inside the LINAC head to take place of the monitor chambers that will not be affected by saturation and loss of charges. And you have also to define procedures to be sure that each and every new machine that will be delivering flash treatments are fully operational and deliver exactly the dose that they have been set to deliver. That's it. We have come to the end of this presentation. I would like to thank you for listening, and that's it.